All right, here we go with some more of this new form of the equation we've kind of built. It's going to be called vertex form, so that's in the heading there. Here we go. So this form of a quadratic we have from all the transformations. This form is where you can see all of the transformations that have happened, right? It's actually called the vertex form of a quadratic. So the question might be, to help you remember it, why does it make sense to call it the vertex form? And I think if you look at it, you'd analyze this and say, okay, it's moved over to the right. It's backwards, right? Over to the right, H. And it has moved up. Okay. So let's go up K or whatever. And so the vertex would have moved over H and up K from 0, 0. And so it's going to end up at that value, right? So the vertex is easy to see from that form. So basically from this, you could see the vertex is a little bit of a space there. Vertex is this HK value, right? So I'll stick with the colors I had there, HK. So you just have to keep in mind the brackets backwards stuff so that you get the right value for the X. So with this example on the bottom, what would you predict the vertex would be? Should be able to look at it and say we're moving to the right 3 and up 5, and so the vertex is going to be at 3, 5. Right? So that's what this says down here. It says that we're going to the right 3 and we're going up 5, and so we end up at a vertex of 3 and 5. Right? So that's vertex form. Get to be comfortable with it, get to know it, and certainly it's the handiest version. It's the nicest version because you can tell so much from it. Right? Compare this to what we started with the standard form, and we found from a standard form of the equation you really had no idea where the vertex would be, which is a really important spot. This one you can tell the vertex at a quick glance, just with that slight little trick to do with the negative of the X value. So here we go. Here's another example. So describe the transformations that would be applied. So we could say that the 7, of course, it'd be really tall and skinny, so it'd be vertically stretched by a factor of 7. So it'd be really tall and skinny. This would be over to the left 5. So shifts left 5. Make sure you recognize here that we're noticing that it says plus, and so we're making it backwards. So what we maybe think. And then this one here, of course, is -3, so it shifts down. Down 3. Okay, so based on that, if you had a vertex let's do this. Let's think of the vertex is normally at 0, 0. Right, so this is the normal vertex. And so we're shifting to the left 5 steps. 1, 2, 3, 4, 5, and up through down 3. 3. So it's going to go over left 5 and down 3. So of course the vertex, the new vertex, is going to be down here at -5, -3. Right? So our understanding of the vertex form and all of those transformations that we've worked hard at helps us be able to get a lot of information from the equation directly. All right, so next step here. Quadratic is, if you're looking at information that you're given, and you should be able to write the vertex form equation from that as well. It's kind of backwards, right? Instead of starting with the equation and being able to describe the transformations, if you're given the transformations, you should be able to write the equation. right? So you just make that page for us to work from. So quadratic flipped upside down. So first of all, right there, flipped upside down, we know we're going to have a y equals a negative x squared, right? Right there. But then we also add into it, and it's compressed vertically by a factor of 2. A little bit of a trick there, compressed, right? So we're dividing, we're like multiplying everything by a half. So we're going to have a 1/2 in here. Okay, so 1/2 x squared so far. Then we need to have what next part here, vertex. The vertex is at a value of -3 and x value of -3. So that means it's been shifted to left 3. So we're going to have the equation look like what? We're going to have inside of the x. Let me try and do it this way. The x itself, right, would have to be, x plus 3. Make it go to the left instead of x. Then the outer part here, we have to be shifted up 5, right? So it's shifted up 5. And so we're going to have an add 5 out on the end. So really, the overall equation then becomes the y equals the -1/2 x plus 3 squared plus 5. So hopefully that kind of makes sense when you look at each piece bit by bit. Here's another one to practice, very similar stuff. So I'm kind of given the information here in a graph instead of in a paragraph. So if you're looking at this, what can you tell? Well, let's do the shifts first, okay? So, because they're easier to tell. So you can tell that it has been shifted over 4 and up 3, right? So it's kind of shifted to the right 4 and up 3. And I almost want to put right 4 like this, as we've been doing when we were working the other way around. So when I say right 4, we're going to make sure to do that correct, right? So let's go right here. So it's horizontal, it's 4 to the right. And so we're going to have a x minus 4 squared. And minus, or to the right is the negative part. And we have an up 3, so we're going to have an x squared plus a 3 as a part of it, and we'll combine all these in the end, I guess. But the vertical part's that. So if we're looking at, if we wanted to combine those for now, totally could. So we'd say, so far, we'd have y equals the x minus 4 squared plus 3. And then we'd have our vertical shift, or vertical stretch. Not shift, vertical stretch. And so we have a vertical stretch. If we look at the shape of this one, okay, so if we focus on the shape of it, we look here and we see that it goes over 1, up 1, and then over 2, up 3, just like normal, right? So 1, 1, and then 1, 3, and so on. It's a normal shape. Okay, so because this thing's a normal shape, you can see that it's going to be the normal graph. If it had have gone, say, over 1, up 2, then we'd have a factor of 2 in front of it, or something else, okay? Whatever number's there. So in the end, we can say this is done. We've got our graph, or our equation, for the graph. Would be that. And so to tie back to things you probably saw in grade 10, kind of nice to go back and say, like, you might have done quadratic matches in grade 10 and done quadratic regressions and so on. So from this picture, if we had this grid superimposed on it, we could identify the vertex really easily as being over 2 and up 4. And so from that, we should be able to put into the equation format. Think of the equation format as having numbers here, here, and here that we can just put numbers into, right? And so over to the right 2, well, I'm going to put a plus, or not plus, to the right 2, going to be a negative 2, right? So we're going to have an x minus a 2. Let me put actually one more thing here as a way to think of this starting out, that you're always going to have the x in there too, right? So you're going to have y equals something x, and I could write it like this, but then I'll just have to write another line. But you have numbers in those key spots, of course, right? So my next line, then I'd say, okay, y, I've got my minus 2, right? So I'll put the information in we have. So we got the minus 2, and everything else is still there. And then we have the up 4, which is easy to do as well. We've got the up 4, so I'll color code this, up 4, and so up 4. And finally here, for the pattern or the value we're at, notice that if we go over 1, we're going down, you have to approximate here, but maybe it's like down a quarter or something, right? So instead of going all the way down a 1 step, it's going down 0.25 or a 1 quarter, and it's upside down. Okay, so I would put, let's do this as purple here, right? So this is down, 1 quarter or 0.25, right? So if we say negative 1 quarter, there, that should be a pretty good match. And if you were to graph that equation, you could see if it would match. So this is stuff we'll do soon as part of the course, but I'm just kind of working at given a picture and so on, so that the next step would be to take a picture, put it into a tech program, right? And then graph that equation and see if it matches, right? If we had it looking like this, and then we graphed the equation, it should match. And then we could fine tune it from there if it doesn't match out on the far edges. So that's the idea. This one here, same deal. If you look at where the vertex is, look like it's over 1, up 5, and approximate the stretch value and the shift value and so on. You'll get an equation just like that for this one as well. So you do that on your own, check your work and so on. And the final one I wanted to point out is just really hitting the idea of the values that we can tell from the Vertex form and what they mean in the context of an application or a situation that has this quadratic shape, and we're wondering about key values, right? So from Vertex form itself, we don't even need the picture anymore. We can determine when the ball reaches the maximum height, because this picture, if we think about what it would look like if we did graph it, it's going to have an upside down shape. The vertex is over 2 steps and up 21. So this is 21, this is 2, the vertex is here, and so on, right? And so roughly speaking, at least anyways, we can just sort of draw it like this and then try to figure out details other than just the vertex that we've kind of established. But from the vertex itself, I just wanted to do that for now, because we can see that it is after 2 seconds. Notice the time is given in seconds since it was thrown. So at time 0 it was thrown, and so on. So for now, for sure, we know that it was after. It takes 2 seconds, right? So determine when the ball reaches. Say at 2 seconds. Determine the maximum height it reaches. Well, the maximum height it reaches is this 21, of course, right? So the max height is 21, and it was in meters in the information. So I suppose I should model the kind of quality I want from your work as well here, where we'd say the maximum height is 21 meters, which really is the y value of the vertex. And if you wanted to be more straight, I guess it's the h or the y value, right, of the vertex. That's a nice answer there. And then this one would have been at 2 seconds. So it reaches maximum height after 2 seconds. which is, of course, the t or x value of the vertex. And then determine the height the ball was tossed from is a bit new. Notice on the graph here, I kind of wasn't sure about this. I just said graph it for now and we can figure it out, right? Well, how would we do that? We would plug in a value for when it was tossed, right? Well, we know it was tossed at time 0. So our equation, h equals -5 t minus 2 squared plus 21, we're going to set t equal to 0. Okay? So if we set t equal to 0, we need to calculate what that'll give us. So we'd have a -5 times a -2 squared plus a 21, which gives us -5 times a 4. So it becomes a +4 because we're -2 times -2. Gives us +4, right? -2 squared equals that, which equals +4 plus 21. So it gives us a -20 plus a 21, which gives us a height of 1 meter. So this number here should be actually a 1. Okay, so the conclusion is the ball was tossed from height of 1 meter. Okay. Now, the last thing here is we're going to use our technology like we did before. And if we were to graph this thing, I wasn't supposed to have that picture on this page, but this is what the picture ends up being once you graph it with GeoGebra. Might still have that GeoGebra page open up here. So you just put the equation in and you see that it lands, around 4. Is it exactly 4? Let's go to our special points and we'll have our zeros of, that's actually 4.049, right? Based on that. So that's what we could say. Now, for now, we're taking that as an estimate from a graph. So 4.049 seconds, it lands after it lands after 4.049 seconds. We're going to see how to do this ourselves with math. Right, with math processes and skills, rather than relying on a computer to do it for us and have it be something we don't know how to do ourselves as human beings. Okay, so that is that. So I'll save that and I'll post that and so on for you. And post questions if you have any, for sure, as always. Okay.